Okay, so for this first video for gases, there is mostly a review here from IntroChem, but there will be a little bit of new information with gas laws, but it'll seem very familiar. The first thing is we've got the conversions for pressure. So we may not be as familiar with the units of pressure, but atmosphere is the standard unit, abbreviated ATM. The millimeter of mercury is the height of the mercury column that's used to measure atmospheric pressure. And a torr is short for Torricelli, who invented the machine that tests our air pressure. So anyway, the torr and the millimeter of mercury are the same thing in terms of, it's a 1-to-1 ratio. But I do want you to remember that there are 760 torr or 760 millimeters of mercury in one ATM. All right. Now, the first of several laws, we're going to have tons of formulas in this chapter, which is kind of nice, right? Formulas make it nice, but keeping straight and knowing which to use where and memorizing your formulas might be a little bit harder. But the first one is familiar. It's Boyle's law. It looks at the relationship between pressure and volume of a gas. And I think we're familiar with this. If I have, let's say, a container that is 5 liters in space, and I've got my moles of gas inside. When I expand that to let's say 10 liters of space, and I still have my same moles of gas inside, as volume increases, the pressure is going to decrease. And pressure is really a measurement of molecular collisions. So the more space you give the gas molecules, obviously the less they collide with each other, and the less that they're going to collide with the walls of the the walls of the container. So as volume goes up, pressure goes down. That is an indirect relationship, and that is captured in Boyle's law, which is P1V1 equals P2V2. So first example here says we've got helium gas at 535 milliliters of space, pressure of 988 torr, 25 degrees Celsius is the temperature. If the sample is transferred to a 1.05 liter flask at the same temperature, right, what will be the new pressure in the gas? So if temperature doesn't change, then it's not going to have any effect on the volume or the pressure, so we can ignore it. That just means we don't need to worry about temperature. So I have an initial volume of 535 milliliters. I've got an initial pressure of 988 torr. I've got a new volume of 1.05 liters, and I want to know what the new pressure is. And when we use Boyle's law, the units really don't matter. They're not restricted like what we're going to see when we get to the ideal gas law coming up in the next video. But what you do need to make sure of is that if you are using V1, V2, right, you're looking at those two units, they have to match. It doesn't matter which you choose. They could both be in milliliters or they could both be in liters, but they have to be in the same unit. So I'm going to go ahead and take my V1 and divide it by 1,000. So my P1 would be 988 torr. My V1 would be 0.535 in liters. P2 is my unknown, and my new volume is 1.05 liters. So I'm just going to divide both sides by 1.05, so 988 times 0.535, and then divide by 1.05. Everything is 3 significant figures, so we get 503, and the unit would be the same as the P1 unit, which would be torr. And that makes sense. Volume almost doubled, so pressure almost was cut in half. So volume went up, pressure went down, just like what we would expect. Next question says, I've got a sample of air that occupies 73.3 milliliters at 98.7 kilopascals, 0 degrees temperature. What volume will the air occupy at 4.02 atmospheres? And again, same temperature means we don't have to worry about T. All right, so we really just have initial volume, pressure, a new pressure. We want to know the new volume. So again, this is going to be a Boyle's law question. Let me move this up. So I've got my initial pressure, 98.7 kilopascals. Initial volume, 73.3 milliliters. All right, my P2 is going up to 4.02 atmospheres, and we want to know what the new volume will be. So again here, the pressure units need to match. So This is very familiar from intro chem, but that's the step that they make this a little bit harder, right? So we're still just using Boyle's law, P1V1 equals P2V2, but now in this case, we're going to have to do a little work up front to get our units to match. Now the conversion for kilopascals, you don't need to memorize. I would give you that. So just real quick, I'll take P1, 98.7 kilopascals. Conversion says 1.01.3 kilopascals is equal to 1 atmosphere in pressure. So 98.7 divided by 101.3 is 0.974 ATM. I'll just keep 3 significant figures because that's what my starting measurement was. So now I can plug in. So I've got my P1V1 equals P2V2. I'm solving for V2, so I'm going to divide both sides by P2. All right, so if it helps, move the formula around first. So I've got my P1 in ATM of 0.974. My initial volume was 73.3 milliliters. I'm going to divide that by my P2, which was 4.02 atmospheres. And what I can see is since pressure went up from P1 to P2, volume should be going down, but I'm going to calculate that, 0.974 times 73.3, and then divide that by 4.02, and I'll keep 3 significant figures. I get 17.8 milliliters. So volume went down, pressure went up, just like what we would expect. All right, so in this one, we have initial pressure in kilopascals. Again, just to make sure, don't worry about memorizing that conversion. I would give it to you if you need it. But I did have to change that really quick to atmospheres to match my P2. But you could have changed P2 to kilopascals, but as long as they match, right? That's the only restriction. And then I've got my P1 in ATM times V1 divided by P2. Now my units of ATM cancel out. So my V2 ends up with the same unit as V1, so 17.8 milliliters. So these questions probably seem pretty familiar, again, just making them slightly harder with the unit conversions. Charles' law was another type of question we looked at in intro chem, and this one looks at the relationship between volume and temperature. And most students know this kind of intuitively, that if you heat a gas, right, you raise the temperature, it will expand. So what that's saying is that if I increase temperature, the volume is also going to increase. All right, that's a direct relationship, right? As one goes up, the other goes up. And that is expressed differently than what we saw with pressure and volume. That is this relationship here, V1 over T1 equals V2 over T2. So this is your Charles' law. Now, unlike Boyle's law, the units here are a little bit pickier. Temperature must always be in Kelvin. So I gave you the temperature conversion formulas here in case you needed to remember those, but you always have to be on the Kelvin scale because you can't have a negative Celsius temperature and you can't have a negative Fahrenheit. And I don't know why there's 2 equal signs here, sorry. So it's V1 over T1 equals V2 over T2. But just make sure temperature is always in Kelvin. So first question here says, I've got a sample of hydrogen gas occupying 692 liters of space at 602 degrees Celsius. If the pressure is held constant, right, that means we don't have to worry about it. What volume will the gas occupy after cooling to 23 degrees Celsius? All right, so I've got a volume at a temperature, so there's a set V1, T1. I've got a new temperature, and I want to know the new volume. So V1, T1, V2, T2 is all I'm going to need here. My initial volume, 692 liters. My initial temperature was 602 degrees Celsius, but automatically I'm going to add 273. The 0.15 won't help me or hurt me because I'm going to round it to the ones place anyway, because 602 only goes to the ones place. So I'll keep this to the ones place, 875 Kelvin. All right, V2, I don't know, it's what I'm looking for. And T2 would be 23 degrees Celsius, again, add the 273. So really that's 296 Kelvin. All right, so I've got my formula, V1 over T1 equals V2 over T2. I'm solving for V2, so I'm going to multiply both sides by T2. Cancel that over there. So now if I plug in, T2, 296 Kelvin, times the initial volume of 692 liters, divided by my initial temperature of 875 Kelvin. So if I take my 296, multiply by 692, and then divide that by 875, I'm going to keep 3 significant figures, and I get 234. Kelvin has canceled out, and I've got liters, same unit as V1. And you don't want to be thrown by the 23 degrees Celsius. The Kelvin temperature is what we use for our problem solving, and that has a 3 significant figure value, because when you add, right, we keep the decimal place of the original. So because really T2 is 3 significant figures, we want to keep everything at 3 sig figs for the answer. All right. Now this question might be a little bit harder just for the algebra, but it's the same. We've got a 575 milliliter sample of carbon dioxide at 602 degrees Celsius. We want to know the temperature that we should heat this to occupy a space of 22.4 liters. So initial volume 575 milliliters, initial temperature 602 degrees Celsius, again just automatic, add the 273. So I'm going to have 875 for Kelvin. And then I've got the V2 is 22.4 liters, and then T2 is what I'm looking for. All right, and again, your volume units have to match. So milliliters go to liters, or liters go to milliliters, whatever you prefer. I'm just going to go ahead and divide V1 by 1,000, so it's really 0.575 liters. So in this case, I've got V1 over T1 equals V2 over T2, but I need to solve for T2. So I'm actually going to move T2 over to the left side, and then what I'll do is I'll move V1 over to the right. So I'll divide both sides by V1, and then I'm going to multiply both sides by T1, so it cancels out. So what I end up with here is T2 is equal to V2 times T1 divided by V1. All right, so V2, 22.4 liters, T1, 875 Kelvin, divide by V1, 0.575 liters. And if we think about it, volume went way up, so temperature should be going way up as well. All right, and what I get here for T2 is a very large number, 34,100 Kelvin if I keep 3 significant figures. So I had my initial volume of 0.575 and my initial temperature in Kelvin of 875. And then my volume went up to 22.4, and so my temperature had to also go up quite a bit, right? Volume, that's a factor of, gosh, like, I don't know, over 40 times 40, so the temperature is going up by about the same amount. So temperature to 3 significant figures, 34,086, so I rounded that up to 34,100 Kelvin. All right, so when I take Boyle's law and Charles' law and combine them together, I get what's called the combined gas law, right? So here's Boyle's law, P1 V1 over T1. Then there's Charles' law, V1 over T1 equals V2 over T2. So combined together, they make the combined gas law. And so what I always suggest is say, okay, I'm going to use this formula anytime there's a change in conditions. So anytime something is heated or the pressure changes or the volume changes, this is my formula of choice. And so if I go back to the first page, right, I could have approached this first example problem with that formula, right? So if I was looking at that first example, P1 V1 over T1 equals P2 V2 over T2. And then when the question tells me that the temperature doesn't change, then I could just cross it out, right? Because I know it's not going to have any effect on my problem, on my pressure or my volume. So same thing with the next example, right? I can see that my pressure is changing. I want to know what happens to volume. So since I'm having a change in conditions, I can start with that combined gas law. And then when I look at that, it again says the same temperature. So that means temperature is going to cancel out, right? And I just have now a Boyle's law problem. But anytime there's a change in conditions, I would say start with P1V1 over T1. All right, third example here, we had hydrogen at temperature, pressure, one more time, at the volume and temperature, and we want to know volume at a new temperature. So because there's a change in conditions, we could start with the combined gas law, and then when it says pressure is held constant, then all we do is cancel out P1 and P2. Right, and then that now is our Charles law. But rather than looking at each of the three laws, memorizing each of the three laws separately, just memorize the combined formula. And if any variable is held constant, then that means we can just cancel it out. So in this last example for the video, we've got an aerosol container that has a gas at 2.5 atm and a temperature of 22 degrees Celsius. And it says, would the container rupture if the pressure exceeds 8 atm? And we want to know what temperature would that happen, right? Is it a pressure? Will it rupture and at what temperature? It doesn't give us a volume. So the idea is that we've got a volume of a container and we want to get right to that point where it might rupture. So we're going to assume that V1 and V2 are equal. And at that point, past that, with temperature, the temperature would have to be greater than whatever value we saw for. Then we know that the aerosol can would rupture. So we've got P1 V1 over T1 equals P2 V2 over T2. And again, since we're assuming volume is just at the point right before rupture, right? Volume won't change until we exceed this temperature. So we'll get rid of V1 and V2. And then all we have to do is kind of worry about our units, right? 22 degrees Celsius, if I add 273, that's really 295 Kelvin. So there's my T1. So now I can solve for this. I'm looking for T2. So again, kind of like we saw in the last example. There's a couple of different ways of doing this. The other thing I could do instead of moving everything around like I did is when you have a formula, you can just flip it. So this is the same as T1 over P1 equals T2 over P2. And then if I'm solving for T2, now all I have to do is multiply both sides by P2. So solving for T2, my P2 was 8 atm. My initial temperature was 295 Kelvin. And my initial pressure was 2.5 atm. All right, so this will tell us the temperature after, right when we get to that at 8.0 atmospheric pressure. So 8 times 295, divide that by 2.5. I'm only going to keep two significant figures here because of the 8.0. So I have 940 Kelvin. And that would be the temperature at which the can would rupture. So if I heated it up more than that, the can would rupture because we would be past that 8.0 atm. And then, of course, at that point, the volume would change drastically if it ruptured. All right, so that's a good place for me to stop for this first video.